We talked about one sample t-test, and in the one sample t-test, the key distinction is that we're comparing a one mean to a standard or to a reference, right? That's a one sample. So you have the mean from one sample, and then you're comparing it to a reference. And that reference is up to you how you come up with it. It might be maybe like in the example that we saw, the usual intake is a reference, right? It might also be maybe a standard. Say maybe someone might say the mean sodium concentration in adults tends to be this value. And so you want to compare the value in your own population to that standard, right? So different ways to come up with that standard. We talked about this, and we will talk about the use of a standard again when we talk about Z tests very shortly. Then we went to talk about the paired t-test. And the key here in the paired t-test is that you have paired measures. You have a measure, you have a measure that is assessed at more than once in a group of people, in the same group of people. Okay. And that same group of people, and that same group of people is, and that same group of people, it might be that you're measuring you're taking that measure and after. So examples are like systolic blood pressure before and systolic blood pressure after, or body weight before an exercise program versus body weight at the end of that exercise program, if you want to see whether that exercise program is effective. All of this is very intuitive, and the key learning from this course, which is the point that Dr. Matara made that day, is what we're really trying to teach you is to just have to understand when to use what, okay? Because ultimately, the way that the world works today, you can figure out a lot of things on your own if you're curious. So what we're helping to do here is lay the groundwork for you to do your own extra work. So that's paired sample t-test. So now you know what paired measures are and when we're going to use the paired sample t-test. And the key reason why we care about why we don't treat the paired sample t-test, why we treat the paired sample t-test differently from the independent sample t-test is because in the paired sample t-test, the values are correlated. If you know the baseline sample, you're likely to be able to guess to some extent the sample at the follow-up time point. An example of that in body weight, for instance. So the person tells you that the mean body weight today is 100 kilograms, and they'll go into an exercise program that lasts 6 weeks, right? And you're asked, what do you think their body weight at the end could be? You could make a good guess and say, if this exercise program is very effective, maybe their body weight is going to be 90 kilograms, right? So you can make a guess about the person's weight at the end based on what you know about the person's weight in the beginning. This is what makes the measure paired. And because those measures are correlated, right? Knowing something about what one measure tells you something about the second one, it means that you have to carefully, you cannot use independent samples t-test, right? The basic assumptions of a t-test are broken. So you need a modification, and that's why the paired sample t-test is introduced. And that's distinct from the independent samples t-test that makes the assumption that knowing about about the measure in group A might not tell you anything about the measure in group B. Okay, and these are usually not the same group of people. These are often in a trial, right, where one group gets the antihypertensive, the other group does not get the treatment, right? And so unless you know how effective the treatment is, you cannot reasonably guess what the blood pressure in the treated group is going to be because you know the blood pressure in the untreated group, right? So this is the key point. So that's all that we discussed last week. Went through a lot of detail about it, and then we walked through the SPSS output as well. So today I want to talk about ANOVA and spend a little bit of time on ANOVA, then switch over to comparing proportions and means. I heard some things. Does somebody have questions? Okay. All right. So we talked about comparing means just now, and we said that in comparing means using t-test, what we're trying to do is compare two measures. Okay, we're comparing two measures, either the mean in the beginning and the mean at the end, or we're comparing the mean at the end in two groups. Okay, like such as what we will do in a randomized trial. In some cases, what we're interested in is not two groups, it is 3 or 4 or 5 groups. In those cases, you cannot use the t-test because the t-test requires that there should be two groups. So a good example of this is in a studies population, so you're trying to find out what the hemoglobin at delivery is in those who are underweight versus those who are normal weight or overweight. Okay, so the hemoglobin concentration in this group of people could be related to each other, could be different significantly. But if you look at these plots that we're seeing here, okay, can somebody tell us how they're going to read these plots, this on the left hand side? Anyone? Just unmute yourself and this one. What do you think? Just looking at plots.
So there's higher hemoglobin. It's the mean hemoglobin for underweight is higher.
Yes.
Normal and overweight is here.
Very good. How about what do you think about the interquartile range?
It's also wider in the underweights.
It's also wider in the underweights. Okay, so the interquartile range is also wider in the underweight. Very good. How about these points? What are they called?
Outliers.
Outliers. Very good. These are called outliers. Very good. Thank you very much. So let's look at the second example. In the second example, we're comparing systolic blood pressure in group 1, group 2, and group 3. Okay, so these three clinic groups, we're comparing the systolic blood pressure amongst them. Can anybody tell us how you will understand systolic blood pressure in these groups? Anyone?
Okay, systolic blood pressure is the mean systolic blood pressure is highest in group 1.
Yes.
Compared to group 2, and then group 3 has the lowest mean systolic blood pressure.
Very good. Very good. Okay. How about the interquartile range? Do you think that you can make any meaningful difference? Can you just by eyeballing, can you see differences?
No.
No, it's hard to see. Very good. And the same thing with there's one outlier, right? Okay. All right. Thank you very much. Now,
sorry, the only thing I would add is that those are medians and not means, right?
So this value here is the mean, right?
So we have interquartile ranges, but we have a mean in the middle.
You have interquartile range, and then you have the mean in the middle. And the distance between the mean, this line that runs through, can usually tell us about where the degree of skewness that's we're seeing in the data.
I understand that, but I thought that when you're using interquartile range, then that dark line in the middle would be a median as opposed to a mean.
So this line, so basically the how do I describe this? The so the this plot, okay, the reason why we're trying to show, oftentimes you want to be able to see the mean. Okay, I see someone else's hand is up. Okay.
Yeah, sorry. Sorry, before Halima goes, I wanted to say that what she's asking about the median, I'm seeing you making reference to mean. Could it be because just looking at this plot, the first plot that says group one, or even all the plots, it appears that the data is normally distributed, because you would find that the interquartile range is just about the middle of both. Does that make any sense to say that? So would
Yeah.
that
So
justify why we would use the mean?
okay, thank you very much. So let's go back and yeah. All right. So this line, thank you very much for calling that out. This line here in this plot, okay, is the mean and is likely to be the median as well, right? So the line here is the median is likely to be the mean as well, because this is normally distributed, it's not skewed, okay? If you look at this other one, and you're right that this is the median, okay? And because here there's skewness, unlike in this other plot. So you're right. So this is the median, and sorry that I didn't make that clear. So this is the median, and it's likely to be the mean on this plot. But in this plot, right, this is the median, but it's likely to be distinct. As you can see, there is no equality between the ranges, so to speak. Sorry that I might have confused you, but that's the, so this is the mean. So we should correct this because I think it's going to lead to errors. It's going to lead to some confusion. But in reality, when we're looking at this plot, we want to understand what the mean is. But it's hard to do that when the plot itself presents the median. Okay, all right. But in this one where there is no skewness, then this is the median, and it's also likely to be the mean. All right, so in ANOVA, what we're trying to do in ANOVA is that we want to compare the means. Okay, we want to compare the means. And if you have a distribution where there's three groups like this, okay, and there's three means, and you want to see whether these means are meaningfully different from each other, then you use the ANOVA, where there's three or more means. And the null hypothesis when you have ANOVA is that these means are equal. Okay? But in reality, what we're looking at here, we're making the assumption that the population means are equal, going back to the distinction between population means and the sample means, right? What we're trying to test is that the population means are equal, but we only have the sample means. So we're going to make an assumption, all right, that the population means are that the sample mean that we have is estimating the population mean. Okay, but in reality, the null hypothesis is that these means are equal. There's three assumptions that are required for ANOVA, and the first is that these data are normally distributed, that the standard deviations are approximately equal, and that the samples are drawn independently. Okay, so let's go back to this plot. If you, based on what I just said, that in ANOVA, the data has to be normally distributed, do you think that you can use ANOVA for this plot on the right? Anyone wants to take a guess?
Yeah.
Yes.
I Okay, yes. Anyone disagrees? How about this plot on the left?
I think you can do for both of them.
Yes,
Why?
yes, for the boat.
Yes.
Yeah, because there are three groups.
There's three
They have
groups.
three characteristics, three distinct characteristics.
You have three groups, three distinct characteristics. Okay. How about the skewness?
The
You know what?
the sorry, Akikomi the one the speaking.
Yeah, go ahead.
The skewness of which groups they are unified, normally distributed, because the what they call it now, the outliers are not so much. The outliers the outlier the data are not much. So looking at the main, they are both all in the middle.
Okay. How
Yes.
about
Sorry.
the
Okay.
how about the distance between this median line and the edge versus the median between this median line and this lower edge?
Distance.
So do you think that this looks roughly equal?
You mean for the first
No,
for
it
the first
doesn't.
chart?
Yeah, for the first one, yes. For this first.
Yeah. For the underweight, they look almost equal.
Okay,
Almost.
does everybody agree?
No.
Oh, no, they're different.
I
No.
think for the
No, they are not
underweight,
equal.
the underweight is slightly skewed
You know, it's
and would have a larger standard deviation.
okay. The underweight
Um,
is slightly skewed. Okay.
it will have a larger standard deviation because the interquartile range is wider, which means that the values, even though we have majority of the values within the interquartile range, they tend to be spread apart, and that's why the mean would skew towards the higher boundary of the interquartile range.
Okay.
But for the other two, I would want to look at the sample size first for the second group, most especially. So if we are dealing with a sample size of like 50 people, and I can
Yeah.
see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 dots, it already means that 11 of those data points are outliers. So that would definitely affect the mean in the second group. Yeah.
Okay. All right. So thank you very much. So I agree with you that there seems to be some skew in here, right? And just looking at this underweight population alone, it doesn't look completely normally distributed. And we say that to use ANOVA, the data should be normally distributed. Okay. Now, the thing that I want you to bear in mind in looking at these assumptions is that ideally what you're looking for actually is not whether each subgroup is normally distributed, but whether the overall population is normally distributed. That means that you will draw the box and whiskers for one distribution for the entire population, right? And then determine whether the median line passes through the middle. And okay, so essentially what I'm saying is, although for illustration purposes, I can point to you that this doesn't look normally distributed. And so if we're only looking in the underweight alone, okay, you would not use ANOVA. If this represented the full population, you would not use ANOVA. So that's the point. Key point to take away is that for the purposes of determining whether there's normal distribution, it is not within the groups, it is the overall study population. Okay. All right, so 3 assumptions to use ANOVA. The first is that the data are normally distributed. The second is that the standard deviations are approximately equal. I think somebody started to talk about the standard deviations, and I will, yeah, so if you look at the interquartile range, it does look as if one interquartile range is meaningfully more than the others, but you're probably better off calculating the means within each group and then looking at the standard deviation. Okay. And then the third, which is probably the most important one, is that the samples are drawn independently. Okay, so I think someone's hand is up. Question.
Yes, thank you for the presentation. I wanted to ask, if we are drawing the box and whiskers for the second plot, can we use ANOVA for it? That's the one for hypertension.
So the one for hypertension. So let's see. Can you try to answer the question yourself? Do the data look normally distributed? Let's assume that the data is normally distributed based on the full population. Are the standard deviations approximately equal? So let's see. What do you think?
For the hypertension, it doesn't look normally distributed to me.
Which one?
Like if not individually, like the overall
Population.
population data doesn't look normally distributed. That's to me. I don't know
It's
whether.
hard to tell when you're looking across groups like this. So you need to draw the box and whiskers for the full population. Or draw, an easier one is for you to draw the histogram or the density plot. Okay.
Okay, thank you.
Yeah, but you would draw that for the full population. One thing that this might help you do, this box and whiskers, is to look at the interquartile range and see if they are roughly equal. If the interquartile ranges are roughly equal, then the standard deviations are likely to be equal as well. Or even better, you can calculate the standard deviations for each group and then make the decision about the second assumption. Okay?
Okay, thank you.
Yeah, you're welcome. So the first assumption is that they are normally distributed, and I said the best way to do this is to draw the histogram or a density plot for the full population, or to draw the box and whiskers for the full population. Okay? And then the second assumption is that the deviations are approximately equal. So you will calculate the standard deviations for each group. But the third assumption is the most important, and that is that the samples are drawn independently. Can anybody tell us what this means? Anyone wants to try? What did we say about independent samples t-test?
So we don't have a repetition in the groups.
You don't have a repetition in the groups, yes. So it will not be blood pressure in the
So
beginning and at the
sampling
end.
without replacements.
Yeah. Okay, very good. So the other key point is that these analyses are best done in clinical trials. Okay, they are best done in clinical trials because what we're saying in essence is that there is no relationship between the groups. So if you're going to do ANOVA, you would use ANOVA in a setting where you could have used the independent samples t-test, but now you have 3 groups. Okay, and because you now have 3 groups or 4 groups, you can't use the independent samples t-test. You have to use ANOVA. Okay. Any questions? So can somebody tell us when the right time to use ANOVA is? Anyone?
I'll try.
Yes, please.
When you're trying to look at the differences between 3 or more groups, and you have data that are normally distributed,
Yes.
the samples are independent of each other,
Mhm.
and the standard deviations are approximately equal. And the most important thing is that the samples are independent of each other.
Very good. Thank you very much. And I should say that the standard deviations being approximately equal, this is not a strict rule. Okay, so if one standard deviation is 1.5 and the other is 1.8, right? So you shouldn't say, oh, they're not equal, so we won't use it. So essentially, it's not equivalent standard deviations. It is just they're all in the same range. All right. Thank you very much. So that's good. So that's ANOVA. And the rest of the slides really just go through the mechanism of calculating. How do you calculate ANOVA, right? How do you calculate the variance of ANOVA? And I'm not going to dwell too much on this area. Basically, what you're doing in ANOVA is that you're looking at how the groups are different from each other, right? And how each group varies within each other. Okay, let me say that again. You're looking at how the groups are different from each other, and you're also looking at how within each group, how similar the values within each group are. So like in this one, for instance, the values are very similar to each other, okay? But in this chart, for instance, the values here, the three groups are closer to each other than these three groups. Do you get what I'm saying? Within this plot, these values are very similar to each other because you can see how compact that box and with that box is. But between the groups, this plot, these values, these means, these groups are similar to each other, they're not far from each other, unlike in this one where the groups are meaningfully distinct from each other. So what ANOVA is doing is that it's assessing how much of the variability is due to differences between the groups while accounting for the variability within the groups. All right, so there's a lot of complex understanding, not too complicated, but I'm going to skip it over and you can go through these slides. Essentially, you will come up with a value of the between groups mean squares and divide that by the within groups. And then you will use that to get an F statistic. And that F statistic is then the basis for the p-value that you obtain. Okay. If you had this same data set that we're just looking at, if you had a systolic blood pressure, if you had a population like this where you're looking at systolic blood pressure, one group got a new drug, another group got the old drug, and one group got placebo. And this is not a surprising design where you have three study groups. Okay, you might want to actually compare a new drug to an old drug that we already know how it works, and maybe it's the standard of care, but you're also curious in understanding the placebo effect. Okay, and so you have three study groups, and this is more often the case when this old drug is not yet the standard of care. Actually, it's more often the case that you would use this when there's an old drug on the market. We already know it works, but maybe there's some issues with it. We're not completely sure, right? So in this case, you might need to test against placebo as well. So now you have three study groups. And because this is a randomized control trial, right, RCT, because it's a randomized control trial, the groups are independent. Okay. Now you would calculate the between groups sum of squares, and then the within group sum of squares, and use that to derive the mean square and obtain the F statistic, and then read off the p-value. Okay. And in this case, again, the way you interpret the p-value is the same way that you would interpret the p-value for t-tests, like as we've seen in the past. And because this p-value is less than 0.001, we will fail to, because this p-value is less than 0.001, we will reject the null hypothesis. Okay? Reject the null hypothesis and conclude that the means systolic blood pressure across these three groups are significantly different from each other. Question?
Yes, sir. So last week when we were discussing, I don't know, correct me if I'm wrong, the tutor said that this is significance, that we want it to actually not be significant, to show that the variances are equal, that if it's significant, it means that the variances are not equal. Or am I mixing it?
So I don't remember exactly in the context that he said that, but it gets at the issue of hypothesis testing. We will talk about hypothesis testing next week when we talk about inference. But briefly, in hypothesis testing, what we're trying to do is the null hypothesis, which is assuming that there is no difference. Okay. And if there is no difference, it is because the mean and the variance are equal. Okay. And that is based on this null hypothesis. So if you go back to this is null hypothesis, which assumes equality. Okay. Which assumes equality, and the alternative hypothesis, which says at least one population mean is different. Yes. Somebody has a question.
Yes, I think I know where Dr. Jerry is coming from with his question. I think it had to do with in the SPSS class, we were looking at the output from SPSS. And you know that section where you decide which p-value to use based on equal variances assumed and equal variance. It's in the, I think it's in that context that that point was made.
Okay. Okay. Thank you very much.
Yeah. Sorry, doctor, for bringing that up. I think I recall now. That was Bonferroni tests.
Okay.
Just to check that the variance within the values are equal, and equal, not equivalent, but similar. Okay, so pardon me. Yeah, that's not in this context.
Okay.
Bonferroni.
All right. So if you look at the outputs for the t-test as well, you will see that it talks about the quality of variances, the quality of means. So yeah. Anyway, so this is ANOVA. I want to make sure that we have enough time to switch over to comparing proportions and odds. But basically, let's take this quick example. And in this example, just looking to see how much more. Okay. So in this example, we're comparing, so this is the same example. So I think we can just go through quickly. We're comparing the mean systolic blood pressure of 3 patients managed by 3 clinical groups. So you randomly assign 900 patients to the 3 groups and measure their systolic blood pressure. We want to identify the optimal strategies, okay? And just in looking here, you might say that, oh, maybe group 1's systolic blood pressure is higher, right? And the p-value that we obtain from the ANOVA is less than 0.001. And so because of that, we reject null hypothesis. Now, when you conduct an ANOVA, the hypothesis that you're testing is that at least one of the means is different. Okay, and we saw that the null hypothesis is that the means are equal to each other, and the alternatives are at least one of them is different. But you don't have a way of deciding which one is different. And sometimes some people will want you to actually tell us, okay, you're telling us that at least one is different, but which one? And so in that case, you might need to test one group versus group one versus group two, group one versus group three, group two versus group three, and they use this to actually provide more information on which groups are really different from each other. All right, so that's what we're trying to do here in Bonferroni, correct? Using Bonferroni testing. So I will skip this over. Also just mention the one-way ANOVA, and to say that sometimes in papers you come across something called the one-way versus two-way ANOVA. And in one-way ANOVA, I mean, basically everything that I've been talking about here today is one-way ANOVA. When you talk about a two-way ANOVA, which you're likely to come across in, it's more often in animal studies, it's not usual that you will find it in human studies, not very usual. Sometimes you would, but people have often talk about two-way ANOVA when what they're trying to do is they're comparing 2+ categories across 2+ variables. So they're making it a bit more complicated. So you're not just looking at systolic blood pressure, you're also looking at maybe blood sugar, right? Something like that. So so that's one-way versus two-way ANOVA. I have never used it in my life. Very unusual to use, and especially in this test, some of these tests are more often these days historical, in the sense that there are newer ways, not necessarily newer, the advent of computers allows you to use alternative approaches that addresses some other challenges that these tests might not address. And as we proceed in this class, you will come across some additional methods that, for us to be able to teach you those methods, we'll show you the flaws of these methods that we have been teaching you to date, and why those more advanced methods are more often the tests or the methods that people use in scientific papers. Okay? There's one group of tests that we have not talked about. I don't know if maybe Dr. Motera talked about it while I wasn't paying attention last week, but those are non-parametric tests. For each of the parametric tests that we talked about, parametric tests meaning that they care about the distribution. These are tests that require you to have normal distribution. And you remember that I was saying that to use ANOVA, the data has to be normally distributed. But that's actually the same thing with the t-tests that we saw. The data has to be normally distributed to use the t-test. But there is a counterpart for each of these tests that does not require normal distribution. So if you have data that looks like that, okay, or that looks like this, where the skewing is obvious, okay, you can use these alternative tests. Wilcoxon rank sum or the signed rank are alternatives to the t-tests. And the Kruskal-Wallis test is an alternative to ANOVA. What these tests do is that rather than compare the means, these ones compare the means. These tests, what they do is that they compare the ordering. So it's not quite the median that they are comparing. Instead, what they're doing is that you order the tests from, you order the values from the smallest to the largest, for each of the groups, and then look to see to what extent those orders are different from each other. Today we're using SPSS and R, and so it's just important for you to understand the intuition behind it and to know when to use what. So if the data is normally distributed, you can use these t-tests. And if the data is not normally distributed, you can use these non-parametric tests. And there's a counterpart for each of these tests. If you understand when to use the paired and the unpaired t-test and ANOVA, then you know when to use these other guys, these other tests. All right, so let's take a break and come back in 5 minutes. And then, or maybe we can take a 10-minute break, come back at the head of the hour, and then we can talk about comparing proportions and odds at that time. If anybody has questions,